Welcome to the video lecture by Dr. Biju Vasudevan for the course Calculus 3 Math 211. This is a part 2 video for week number 11 in which we will discuss the chapter 13.6 Directional Derivative and Gradients. Of course, in this session we extend the concept of a partial derivative to the more general notion of a directional derivative. We have seen that the partial derivatives of a function give the instantaneous rate of change of that function in the directions parallel to the coordinate axis. That is, if you are looking for, if you find dou z over dou y, it will be parallel to y axis. If you find dou z over dou x, it will be parallel to x-axis, isn't it? So change in the x rate of change in the x direction, dou z by dou x. Rate of change in the y direction, it is dou z by dou y. This is what we have seen in the previous chapter. Directional derivatives allow us to compute the rates of change of a function with respect to the distance from a particular point in any direction. That's the major difference here from the regular partial derivative to directional derivative. Okay. Suppose that we wish to compute the instantaneous rate of change of a function f of xy. This is f of xy with respect to the distance from a point x0, y0. This is the point 0, y. In some direction. The direction, assume that we are assuming the direction is given by a vector u. U vector is u1i, u2j. When you change the components of u1 and u vector, that is, if you change the values of u1 and u2, the direction changes. There are infinitely many directions. See in the second graph, the right side is showing the way of finding the direction. So there are many ways. If you choose the u with same values of u1, u2 with opposite signs, you will find this direction. That is it. So s is the distance from the point x0, y0 to xy, and we have a formula to find the equation of this line. Assume that this is the line passing through the point p0 and parallel to the vector u. So we have seen the parametric form of the statement, which is x is x0, x, this value of x is x0 plus s times u1, and y is y0 plus s times u2. When s is 0, when s is 0, you will get x and y are xy are equal to x0, y0. So this will happen here, right? So we should remember. Since u is a unit vector, s is the arc length parameter that has its reference point at x0, y0 and has a positive values in the direction of u. Okay. On the line L, the variable z is a function of xy. When you substitute xy is getting a different shape when you substitute the values of x and y in z. See, substitute them in this z. So what is your new z? Z is f of x0 plus s u1. This is x comma y, y0 plus s u2. So now what is happening here? Z is actually a function of two variables x and y, and x is a function of one variable s, y is another function of another the same variable s, isn't it? So here again we can use chain rule to find derivative of z with respect to s. So when you find the derivative for this function and you take s is equal to 0, you get the instantaneous rate of change of z at this point in the direction of u. This is our directional derivative. When you find actually if you find a plane here which is built on the line given, and the plane intersects with the surface z at this curve and creates this curve, isn't it? And at this curve there is a tangent. The tangent line, the slope of the tangent line is the physical meaning of this. The slope of this tangent line at this point is the physical meaning of directional derivative. Okay, so how to calculate it? So now actually this is what I'm going to be given in the formula coming up next. So you can actually go through this video to get the animation of directional derivative. And this formula, as we have seen, we are differentiating the function of x, function of x comma y. This is x comma y, x is x0 plus su1. So when you differentiate the function with respect to z and take z equal to 0, this is the fundamental definition of directional derivative. But we are going to find the directional derivative by using a different formula. That formula will be derived from the same definition. And the definition 13.6.2 says the same formula for a function of 3 variables, and we cannot interpret this one physically, but you can consider this is another, just an extension of the same formula 2 for another dimension. Now let us see how to derive the actual formula that we are going to use for finding the directional derivative. And remember, okay, let's do it here. Okay, let's do it. This is the formula we are looking for. I will show you how to derive this formula. Formula number 4. We know z is a function of x and y. X is a function of s, y is a function of x. So this chain rule we are going to use to find dz over ds, isn't it? This term is dou z by dou x, dou z by dou y. Recall the concept, this concept from the topic of chain rule, isn't it? Here dx over ds is dy over ds. Okay, now the formula for dz over ds is dou z over dou x and dx over ds plus dou z over dou y and dy over ds. We need to find all the 4 terms to be substituted in this formula, then we get the equation number 4. So how to get this one? How to get this one, isn't it? So let me write some more points on this same page. What is z? Z is a function of xy, and when you know that x is a function of s. X is the function of s, which is x0 plus s times u1. Again, y is a function of s. S is the variable here now. The distance, it is the only thing that varies here. And because x0, y0 is a fixed point, u1, u2 are fixed components of the vector. Now the only thing that varies is s. So variable is s, isn't it? S times u2 for y. Now you can find what is dou z by dou x. We call it fx of x comma y. Similarly, what is dou z by dou y? Fy, f subscript y of x comma y, isn't it? This x comma y can further be replaced by the values of equation number 1 and 2. That's okay. So we have fx and fy. So this term in this formula, first term dou z by dou x is fx. The second part, the first term is fy. Now differentiate x with respect to s. From equation number 1 you get dx by ds. First term is 0. When you differentiate s, it is 1. The constant is u1. So this is u1. Fx u1, fy u2. Simply you can get the second part from y. What is it? Dy by ds. 0 plus s. When you differentiate with respect to s, s is 1, u2 is the constant. So u2 is this. So this formula is quite simply du, that is derivative of f, the directional derivative of x at the point x0 y0 is, first we differentiate f of x comma y, not x0, y0, isn't it? With respect to s, and then take s goes to 0. When you find this derivation, you are actually getting fx of x comma y u1, fy of x comma y u2, and when s goes to 0, x comma y will be equal to x0, y0. Go to the basic definition of basic introduction. Actually, what is the relation between x0, y0 and xy? The equation of the straight line. So when s is 0, so actually x is x0 plus s times u1. When s is 0, x is equal to x0. So this term x will be x0 and y will be y0. So obviously this formula has been derived. So very simply, how do you remember this formula? Directional derivative of f in the direction of u is fx u1, fy u2. You can simply remember this one, and you remember u1, u2 are the components of the vector u, unit vector u. Fx and fy are the partial derivatives of the f, the direction of x and y. And then we substitute the values of x and y, x0, y0, to get the final value of fx and fy. That will be easy. So the formula number 5 is just another the extension of the same formula number 4 for another dimension. That is it. Let's see the concept of, and we will express the directional derivative in a different way in this slide. See, this is about gradient. The actual definition, the physical meaning, you can understand by going through the link given in the PowerPoint. And now let me give you an idea. In the three-dimensional space, if there is a surface z is equal to f of x, y, isn't it? Your this is x direction, this is y direction. The x direction there is I vector, y direction there is j vector. The change, if you find dou x by dou z by dou x, it is in the x direction. If you find dou z by dou y, it is in the y direction, isn't it? So the rate of change in the x direction and rate of change in the y direction is given. So what if these two are applied? If you add this vector here, the sum of these two vectors will give you a new vector in this direction. That is, if you take dou z by dou x, I vector, dou z by dou y, j vector, when you consider these two individual vectors and add them, you get a new vector here. This vector is called del z. It is called a gradient. Actually, physically, if there is an object here, one person is pulling this object in this direction, another person is pulling the object in this direction, person 1 and person 2. This object obviously moves in this direction. This direction is called direction of maximum change. So this is what we are finding by the concept of gradient. Gradient of any surface is the direction of maximum change. Maximum change occurs in this direction, minimum change occurs in its opposite direction. Right. Okay. How to do so? This term is called this term okay, this notation, the inverted delta, is called a del operator, otherwise del or nabla, you can call it nabla. This is the notation. Actually, del operator is dou by dou x I, dou by dou y j, plus dou by dou is k. You can write for three-dimensional vector, isn't it? So if we want del f, here the f gets introduced. We differentiate f with respect to x and write along with the y, I. We differentiate f with respect to y and write with j. Derivate f with respect to z partially and then write k. These are partial derivatives of the function that is appearing here, and then ijk will be used. This is the way to find directional derivative of a three-dimensional vector. Not the answer directional derivative, it's a gradient of a three-dimensional vector. isn't it? So gradient is the direction of its maximum change. You remember it, isn't it? That's what here. Okay, now we will see one more beautiful thing: the relation between the gradient and directional derivative. We know directional derivative of f in the direction of u at the point x comma x0 comma y0 is nothing but fx x0 y0. I'm sorry, slightly I need a modification here. When you write, simply you write du of f is fx u1 fy u2. This is actually directional derivative. Well, this can be expressed as the dot product of two vectors. This is actually sum of the products can be expressed the dot product of two vectors. In the first vector is fxi fyj dot product with u1i u2j. Is it clear? u1i u2j. When you find the dot product of these two vectors, you will find this one, isn't it? fxi plus fyj dot product with the u1i. So this is u vector, this is u vector, and this part is nothing but our del f. So del f dot u is the slope of the surface at this point. This point is x comma y comma f of x, x of x comma y. At this point the slope of x, isn't it? So this is directional derivative in terms of the gradient, gradient of the function dot product with the unit vector, given unit vector u, isn't it? So you can find duf in two different ways. Either if you have the gradient of the function and a unit vector, find the dot product, you will find the rational derivative. Or if you are given the function, you just find the fx and fy, multiply by the components of u, sum them up. So there are two. So you should remember that u is unit vector whose length is 1. So when you find absolute value of this one, del dot f will give you the maximum. So you can find directional derivative in any direction, but the direction of maximum change, the gradient, will give you the maximum value of the slope. This is the direction of steepest change, steepest increase, you can say. Okay, fine. Some properties of the gradient. Now, f be a function of two variable or three variables, okay, and p denote, let's discuss it for two variable, just extend the concept for three variable. P denote the point x0 y0. Assume that f is differentiable at this point p. Now if gradient of the function is 0 at the point p, then directional derivative is also 0. All the directional derivatives of 0. Gradient total, that is rate of max direction of the maximum directions is nothing. There is no direction, so there is no change at this point. Directional, the gradient is 0, so all the directional derivatives at this point will be 0 in any direction. You can try. If the gradient is non-zero, then among all possible directional derivatives of p, that is, there at the point p, there are many possible directions, we can say, isn't it? We can say at every direction we can find a directional derivative. 1 directional derivative, 2 directional derivative, 3. For every direction we can write a unit vector and then use that unit vector along with the function in the formula. We can find directional derivative. So, but among all the directional derivatives, the derivative which is in the direction, if this is your gradient, in this direction you can find a unit vector and then find a directional derivative. This directional derivative will be the maximum. The value of this largest directional derivative. So largest directional derivative occurs at in the direction of del f, and its absolute value will give you the value of the larger derivative. So opposite side, in the opposite side you will give minimum value. That is the third point. So the extension of this theorem is given here. Can go through it. Oh, well, what's another point, another property? F the as continuous first order partial derivatives. Okay, f is differentiable at an open disk centered at this is the point. At this point we are looking, this is actually the curve, and I can say that this is the level curve of the function. If z is equal to f of x y, if the function is given z equal to f of x comma y, is level curve is z is considered to be a constant k or c. So this is the level curve of the function, and at this point x comma y comma 0, actually directional derivative is its normal. So for any surface you can find its normal vector by finding its gradient. And when you divide its when you convert this into unit vector by dividing its length, you will find unit normal vector for any curve. The opposite direction is given here. Okay, let's go to the exercise problems. Let's solve these kind of problems right now. Now the question number exercise 13.6. Find directional derivative of u in the direction of directional derivative of f in the direction of u at the point P. Okay, let's solve this one. What is the formula? What is the basic formula? There are two formulas you can use: dot product of the gradient and the u vector. Or instead, let's use the basic formula: directional derivative of u f at in the direction of u at the point P. P is origin, right? We will use it later on. This is fx u1 fy u2. From the u vector, collect the u1. First component u1 is negative 1 over root 10. And then what is u2? Negative 3 over root 10. Fine. fx is given. So from the function f, find fx. Derivate the given function partially with respect to x. So keep y as a constant. When you differentiate ln, it is 1 over 1 plus x square plus y. When you differentiate the function inside the ln with respect to x, you get 0 plus 2x plus 0. That is it. That's the derivative. And now you simplify this one. This is 2x over 1 plus x square plus y. Now this fx at the point P, fx at 0 comma 0. Yes, x is 0, 2 times 0 over 1 plus 0 plus 0, the answer is 0. First term is 0, fx is 0, u1 is given here, fx is given 0. Second part, fy, differentiate the same function f with respect to y. So 1 over 1 plus x square plus y, and then go to the inner function by chain rule. This is 0 plus 0 plus 1. So the answer is 1 over 1 plus x square plus y. Now substitute the point fy at 0 comma 0. 1 over 1 plus 0 plus 0. The answer is 1. So fy is 1. There are 4 terms we need. Fx, which is 0. Fy, which is 1. u1 has been given here. u2 has been given here. So just substitute them in the formula A. You got it, eh? Though let's write the answer here. duf fx is 0. So the first term, whatever u1, it is 0. Second term is 1 time fy is 1, and u2 is negative 3 over root 10. So the answer is negative 3 over root 10. This is the answer. This is the answer of this problem. And then let's solve one more problem to understand the concept, which is a function of 3 variables. Now how do you write the formula for directional derivative duf, which is fx u1 fy u2, fz u3. See, all the given vector is a unit vector. We can verify it. You can find a norm of u and you will end up with 1. You can check it. So if this unit vector, then this formula is valid. If it is not a unit vector, we should convert it into unit vector, right? But in this case it is a unit vector. We can verify. Therefore I have the components u1, u2, u3 from this vector. 2 over 7, negative 3 over 7, 6 over 7, isn't it? So all these three components. Now we are concerned about fx, fy, fz. So differentiate f with respect to x. How do you do it? First term, y is constant, e raised to x z. When you integrate, when you differentiate exponential, it will remain same, and then differentiate the powers. X, we are differentiating with respect to x, so x will be 1, there will be z alone. And second part, z is 0, that is z will be considered as constant. So what is the answer for fx? Which is y z e power x z. Now substitute the point p, fx at the point p, 0, 2, 3. X is 0, y is 2, z is 3. So y is 2, z is 3, e raised to x is 0, then e power 0 is 1, so the answer is 6. This is for fx. Try for fy. Differentiate the function with respect to y. When you differentiate the first term with respect to y, it will be e power x z. In the power exponential, there is no y. Other terms are constant. Second term is 0. And substitute the value fy at the point 0, 2, 3. X is 0, there is no y, x is 0, 0, z is, whatever it is 0. E power 0 is 1. That's done. We got fx, we got fy, and finally fz. We differentiate the function with respect to z. Y is constant, e power x z, and when you differentiate x z with respect to z, you will get x. Plus when you differentiate z square with respect to z, you get 2z. So f is at 0, 2, 3. Y is 2, e power x is 0, 0 into 3 is 0, 0, and x is 0, x is 0. 0 plus 2 times 3, z is 3. So the first term is 0, second term is 6, the answer is 6. So first fx is 6, fy is 1, fz is 6. Therefore, what is the answer of this problem? Now, duf fx is 6 times u1 is the first component, right? That is 2 over 7 plus fy is 1, second component of u vector is negative 3 over 7 plus here fz is 6 into third component, 6 over 7. So here 7 is the common denominator, 12, first term 6 into 2, 12 minus 3, which is 9, plus 36 plus 9, as it is 45 over 7. That is the end of this problem. 45 over 7. So let's solve. The answers have been given here. You can find the directional derivative of p at the point. What is the case here? What is it? What should we do here, or what is the difference it shows from the previous one? The same, there is a function. You can choose problem number. We can choose problem number 14. The point is origin, so substitute x0, y0. That's it. X is 0, y is 0. Here the function is a function of x and y. Okay. The vector, is it the unit vector? That's the question. No, it's not unit vector anymore. Let's make it unit vector. Check the norm of the vector. This is under square root 5 square plus negative 2 square, which is 25 plus 4, which is square root of 29. So the length is not 1, so this is not a unit vector. So we get the unit vector u at first. So any vector divided by its own will give you unit vector. So this is 5 over root 29 negative. This is I. Negative 2 over root 29 and j. This is the unit vector. Though, therefore u1 is the first component, 5 over root 29. u2 is the next component, negative 2 over root 29. Okay, now we need two more elements to write the formula. What is the formula of du? duf is fx u1 fy u2. Fx and we know u1 and u2. We are supposed to find fx and fy. Let's find it in this left side. So fx from the given function, differentiate f with respect to x alone, keep y as constant. X, the first term x, differentiation of x with respect to x is 1, so the constant is e raised to y. Second term y is constant, keep it, e power x will be e power x. This is fx. So fx when point is 0, 0, x is 0, y is 0, e power 0 minus 0 into e power 0. Second term is 0, first term e power 0 is 1, the answer fx is 1. And try fy. Differentiate the same function with respect to y, keep the x as it is, differentiate e power y, it will be e power y, minus keep e power x as it is, differentiate y, it will be 1, so e power x. Now substitute the point 0, 0, x is 0, the first term is 0, minus e power 0, just negative 1. Therefore the formula gives us f of fx, which is 1 times u1, which is 5 over root 29, plus fy is negative 1 and u2 is negative 2 over root 29. So for the common denominator is square root of 29. This is 5 plus 3, this is 8 over 5 plus 3 or 2, 5 plus 2. So this is 7. 5 plus 2, 1 and 2, 3, 1 and 2, positive 2, so 5 plus 2, it is 7. That is the end of this problem. So I leave the similar type problems to you to practice. Find and the derivatives of f. So if there is a 3 variable function, we'll do it one more time. Okay, let's do for problem number 22. Here again it is a function of 2 variables, but you know theta has been given instead of unit vector. You have to find the vector by using the concept of angle and length, isn't it? We are looking for a vector, unit vector for problem number 20. The point is origin, so it's very easy, isn't it? Okay, now a vector v vector can be found if the length and angle are given. Cosine theta, sine theta, we have studied this one before. Obviously if you check theta is equal to pi, pi is opposite side of 0 degree. Then the 0 degree is associated with the I axis, 90 degree is associated with the j axis. So opposite to 0 degree it will be pi, isn't it? So pi will be in negative I, we should get. Now let's try it here. So u vector is norm of u into cosine pi sine pi, and we are looking for unit vector, so the norm of u is 1 into cosine pi is negative 1, sine pi is 0. This is negative 1 0, which is negative I plus 0 j. Therefore your unit vector u is just negative I. You can say that u1 is negative 1 and u2 is 0. This is the information from theta is equal to pi, right? And then find derivative from the given function sine hyperbolic x, shin, you can say shin, cosine hyperbolic cos. Okay, we differentiate. See, when you differentiate, remember that cosine hyperbolic x is e power x plus e power minus x over 2. and sine hyperbolic x is e power x minus e power minus x over 2. So keep it in mind, then differentiate. Derivation of sine x, I am writing here. From this function we are finding fx, derivating with respect to x. So there is sine hyperbolic x, cosine hyperbolic y. We are derivating with respect to x partially, so cos y will be constant, isn't it? Cos at y will be constant. Differentiate sine. Differentiate this term. You can find sine hyperbolic h hyperbolic x will be cosine hyperbolic x without any sign, isn't it? Check this one. So now fx at 0 comma 0, cosine hyperbolic 0, use your calculator, possible otherwise substitute x equal to 0 in the above formulas of cosine hyperbolic and sine hyperbolic. Cosine hyperbolic 0 is 1 into 1, which is 1. Similarly, we will find fy, differentiate with respect to y. So sine hyperbolic x will be safer and differentiate cosine hyperbolic. It will be again sine hyperbolic y without any sign. Therefore, fy 0 comma 0 substitute. So sine hyperbolic 0, again sine hyperbolic 0, when you substitute in this equation number 2, x is 0, you will get e power 0 is 1 minus 1, isn't it? So it is 0. So 0 into 0, the answer is 0. Second part is 0. So finally we will write the answer here. The formula for problem number 22 we are dealing with. The formula for directional derivative is duf. This is fx u1 fy u2. What is fx? Fx is 1 and u1 is negative 1 plus fy is 0 and u2 is fy is 0, u2 is also 0. Thus answer is negative 1. That is it. That's the end of this problem. I think I can leave the remaining problems for your practice. Okay, we need to find a gradient. Let me check whether one more problem is possible. So this problem again, find the directional derivative of the function. This function is a function of three variables. You can find a of x, which is negative y over ex plus z whole square, e of y 1 over x plus z, e of z negative y over x plus z whole square. So in these three results, the partial derivatives, substitute the point p, then you get fx at 2 1 negative 1, fy 2 1 negative 1, fz 2 1 negative 1, isn't it? Three terms will be there, and of course the formula needs a unit vector, and if you have two end points of the vector, you can find pq vector. What is pq vector? Minus 1 minus 2, this is minus 3 minus 3, 2 minus 1 1, 0 minus 1 is 1. This is the pq vector. Now find the length norm. This is not actually unit vector. You have to find the norm of this one. Is it 9 plus 1 plus 1 is under? Therefore unit vector is pq vector divided by its norm. So negative 3 over root 11 I plus 1 over root 11 j plus 1 over root 11 k. Therefore u1 is negative 3 over root 11, u2 is 1 over root 11, u3 is 1 over root 11. You got three components fx, fy. You can just use the formula duf is fx u1 fy u2 fz u3 and get the answer. The answer is on the PowerPoint. Verify yourself, right? Okay, I'm going to the last category of problems from this chapter. Find del z and del. We are supposed to find only directional derivative del operator. Remember, del operator is for two variable functions dou by dou x I vector, dou by dou y j vector. If there is one more component, then dou by dou z k vector, isn't it? Okay, what is del z? This is z, this is actually w. We will do w. And the rest is your work. 34 I'm solving. What is del, I mean nebula w? Wx I vector, wy j vector, that is it. Wx is nothing but dou w by dou x. Here in the first term of the del, the function is if this is f, this is dou f by dou x, this is dou f by dou y, right? Wy is dou w by dou y. So from this equation, find wx, derivate w with respect to x alone. E raised to minus 3y is constant, cosine will be negative sine 5x and 5. So you will find wx is minus 5 e raised to minus 3y sine 5x. What is wy from the given equation? W, differentiate w with respect to y alone. So e power minus 3y repeats with the coefficient negative 3 and cosine 5x remains without anything. Therefore now del w is wx times I minus 5 e raised to minus 3y sine 5x minus wy times I vector minus minus 3 e raised to minus 3y cosine 5x j vector. That is it. That's the end. So this is the formula for del. And del, I mean del w, which is gradient. Gradient dot product with the unit vector will be directional derivative, and you just practice the similar type problems from your textbook and then solve the upcoming quizzes and assignments. Thank you very much.